keep it down, but yeah, so if you hear loud noises, that's probably them. I might have to send them a text or two just to let them know, like, hey, I'm presenting or whatever. But for the most part, they should be good. And with that, we'll go ahead and get into this presentation here. If I can make sure I click on the right thing to share. All right, and then to this one. All right, so everybody can see the presentation, is that right?
Yep, I think we're ready to go.
All right. Minimize this really quick. All right. So I want to thank everybody for coming out to this talk, and hopefully by the end of this, you'll be able to leave having learned a little bit about Alberta paleontology, as well as more specifically about the Tyrannosaur dinosaurs that we can find fossils of throughout the province, and just how these fossils are kind of helping us to reveal, or helping to reveal new things about the biology of these animals and of the ecosystems of late Cretaceous Alberta. So, as stated, I'm a PhD candidate in paleontology in the Department of Geosciences at the University of Calgary. I've been doing research there since 2016 and been working mostly on that group of dinosaurs known as the Tyrannosaurs, but have started to kind of transition into some other dinosaur groups, including Dromaeosaurs like Velociraptor, as well as some other dinosaurs like Caningnathids, and a bunch of other dinosaur projects that I'm hoping to get published on here soon. So when it comes to other paleontologists, I'm quite unoriginal in terms of how I got into this field of study. I'd always enjoyed all aspects of nature, catching lizards, snakes, amphibians, that sort of thing, looking for deer antler sheds or other bones of animals in forests and mountains that I grew up in. And all of that, I also really enjoyed dinosaurs. And so it was kind of only really a matter of time before I kind of got into paleontology or sought paleontology out as a profession. So most of my research actually involves going around to various museums to examine the specimens of Tyrannosaurs and other dinosaurs that have been found, taking lots of measurements and photographs, and writing about features that I noticed that might be useful to identify differences between the species, or to identify features that might be useful for establishing functional limitations or different aspects of the biology of these animals, things like bite force capabilities or range of motion limitations in their limb bones. I also do a lot of work with CT scanning. And I actually CT scan a lot of the fossils that I work with, and this is actually one of my favorite methods when it comes to when I do start doing my research. And so this entails actually sending fossils like dinosaur skulls through a CT scanner and bombarding them with high intensities of X-rays. So much like you get a CAT scan of certain areas of your body to look at internal structures, we often use these same CT scanners to actually look inside of fossils to kind of get an idea of some of the internal features that are going on in those animals without actually having to damage the fossils and cut them open to look inside of them themselves. And so if you know how to work the programs that actually read this data, you can actually create some really cool graphics using that CT data. And so this is a 3D rendering of a Tyrannosaur skull, one from one of our baby animals that I work with. And so this was rendered using data from one of those CT scanners. And so we were actually able to use this to look inside the skull and isolate out the cavity that would have held the brain, so which you can see here in blue. And so this particular specimen is part of a project that's hopefully going to reshape the way we understand brain evolution within theropod dinosaurs, not just Tyrannosaurs, but also including modern birds, and kind of understanding brain evolution on the way up to birds. So Alberta has always been kind of the holy grail of paleontology. Very large swaths of the province host fossils of various ages, and these range from 550 million-year-old animals from the dawn of multicellular life, things such as this trilobite here from the Burgess Shale, to fossils that are much more recent in age, things like woolly mammoths, bisons, horses, and even American lion fossils, which date to only about 10,000 years ago. But Alberta is also host to an absolutely astounding fossil record of dinosaurs and other Cretaceous and prehistoric animals that come from the age of the dinosaurs. In fact, the bedrock of most of the southeast area of the province is made up for the most part of a largely uninterrupted sequence of different rock layers that span the last 18 million years of the Cretaceous period, which was essentially the finale for the dinosaurs. And this hosted hundreds of different species of dinosaurs and other late Cretaceous animals that can be found across the globe. And so people often are, of course, aware that dinosaur fossils can be found in Alberta, but what is often not realized is kind of just how important Alberta is to our understanding of dinosaurs. Alberta is actually one of the best places in the world for dinosaur paleontology. Out of all of the different dinosaur species that have been found around the world, roughly 11% of those have been found in Alberta. And so it's also not just important for dinosaurs. We also have an amazing fossil record of other animals, including giant marine reptiles and giant flying reptiles, as well as some really ancient crocodiliforms. But in addition to having just an abundance of different dinosaur species, there have been some truly amazing fossil discoveries made here, a lot of which have come out in the past few years. For example, a few years ago, my research team found a fossil of this baby ostrich dinosaur that we call an ornithomimid. And so what's particularly important about this fossil was that in addition to the bones themselves being preserved, it also preserved these long brown filament-like structures all around the outside surface of the body. And so it was found that these structures were actually the fossilized feathers. And this made this the first discovery of a dinosaur with fossil feathers from anywhere within North America. And so this actually led to a big re-examination of some of the other ornithomimid fossils that had previously been found in the province, including some of these larger individuals of that same species. And what they found in those was that if they looked at the forelimb bones of those things, they actually found these little black markings along the forelimbs there. And these looked a lot like what we can see in modern bird bones. And so these actually correspond to the roots of the feathers and how the actual wing feathers and that would have rooted into the down towards the bone. And what's important about this is that they weren't actually able to see these same structures on that younger juvenile animal. And so this suggests that these long wing feathers probably didn't actually develop until these animals had reached sexual maturity. And this is important because these animals did not have a body form that was capable of allowing flight at any stage in their development. So the fact that we were seeing evidence of these large wing feathers lends to this idea that wing feathers themselves did not originally evolve for flight in theropod dinosaurs, and probably initially evolved as a means of display, and that flight was a behavior that came along long after wing feathers had already been acquired. We also have some other amazing discoveries in the province in the past few years, and these include these mummified armored dinosaur known as Borealopelta, which you may have seen and heard about in the news. And this particular fossil was really important because it actually preserved much of the skin and other soft tissues around the body. And so within the skin, we've actually been able to find these tiny little, or take some microscopes and look at these tiny little fossilized pigment cells known as melanosomes. And these are actually give us an indication of what kinds of colors this particular animal might have been. And so they actually were able to reconstruct what the color might have actually looked like. And these seem to be that there was mostly covered in these very rusty red colors. And so they gave it this illustration here that actually seems to be a close representation of what we think this dinosaur might have been colored like, with these more pale colors coming out along the belly there. And so all these kinds of discoveries, of course, raise the question of why Alberta is such an amazing place to find fossils. And the answer to this has to do with the environments during which these animals were buried. So from around 77 to 66 million years ago, the world was a lot warmer than it is today. You had the Rocky Mountains that had only just been built up, and we also had a large seaway that stretched from the Gulf of Mexico all the way down to the Arctic Ocean. And this led to a lot of rainfall going down across Alberta. And from that, we had a lot of sediment runoff coming from those very young Rocky Mountains. And this was very important for dinosaurs in two ways. For one, it led to the sediment runoff led to a very extremely nutrient-rich lands, which were perfect for plants and led to a very lush tropical forest ecosystem to begin developing. In addition to that, it increased the sediment runoff from those mountains, which also provided lots of opportunities for dinosaurs and other organisms to get buried. So we had this kind of perfect situation of a high enough burial rate in addition to a high enough density of organisms that lived in those environments. And because Alberta is much drier today, it's actually led to the formation of these badlands throughout the province. And so this has led to a lot of rock exposure. And so this is important because it allows us to actually go out into badlands and actually start to look for fossils because we have such high rock exposure. So we have lots of opportunities to find fossils of dinosaurs and these other organisms. And so we have a perfect situation all the way around that essentially beats out just about anywhere else in the world in terms of the density of that dinosaur fossil record and how and just how easy it is to find fossils there. And so those rocks host a very diverse assemblage of dinosaur fossils, which range from small raptor-like dinosaurs like Sornitholestes, Langstonii there, to much larger dinosaurs like duck-billed dinosaurs like Parasaurolophus here, and horned dinosaurs like Triceratops, to even non-dinosaurs, including small mammals, turtles, crocodiles, and even on rare occasions, fossils of some truly bizarre flying reptiles known as pterosaurs. And some of these were even large enough to have wingspans that reached roughly 10 meters in length. So these things were literally the size of a small plane. Now, of course, to the benefit of my research, Alberta also has fossils of these giant apex predatory dinosaurs known as the tyrannosaurs. And so tyrannosaurs were the largest predators, or some of the largest predators to ever walk the earth. And so with species like Tyrannosaurus being members of this group, these are, of course, being very famously known dinosaurs. But despite how famous they are, these animals were actually quite bizarre in terms of their anatomy. Even with regards to other large medium dinosaurs. Tyrannosaurs had abnormally large skulls with these small forelimbs that only had 2 fingers on each hand. And with respect to their body size, their jaws were extremely robust. They possessed some of the highest bite forces ever known among land animals, and actually most animals in general, including some of the ones that we can actually find in oceans. And so to facilitate and deliver these powerful bite forces, the jaws were lined with these absolutely massive teeth, which were thick enough and strong enough to crush the bones of their prey. And so for a visual comparison, this is the tooth of an individual T-Rex that wasn't even fully grown. And I'm a fairly large person. I'm 6'4", so you can kind of get an idea of how large this tooth is. And this individual is actually only about 75% of the way to full size. And this tooth actually came from closer to the front of the jaw, so it wasn't even its largest tooth. So you can kind of get an idea of how large these teeth would actually have been during life. But in addition to just having these really large teeth and these really large jaws, we also see a lot of other features within the Tyrannosaur skull that help to drive home just how much these animals were built for power. In most dinosaurs, the nose was bridged by 2 separate bones known as the nasals. But in Tyrannosaurs, these bones were actually fused into one single bone, and this helped to redistribute the stress of biting, which helped to strengthen the skull. And so you can kind of think of this as analogous to a keystone within an archway, which kind of helps to distribute the stress of the arch itself. And so Tyrannosaurs had a whole bunch of features within their skulls, which kind of helped to facilitate those incredibly powerful bite forces. So they truly were animals built for bone-crushing bite forces. So Alberta actually has one of the best fossil records, arguably the best fossil record of Tyrannosaurs relative to anywhere else in the world, both in terms of the number of species that can be found here and the total number of Tyrannosaur fossils that have been found. And we also have some of the best preserved Tyrannosaur fossils, with several nearly complete skeletons having been found in the province since field work began in the early 1900s. And so historically within Alberta, we've had fossils of 5 different species of Tyrannosaurs, including the largest and most famous Tyrannosaurus rex, but also several other species like Albertosaurus sarcophagus and potentially others like Gorgosaurus abratus and Displetosaurus. Now, of course, the most famous of these was Tyrannosaurus rex. Tyrannosaurus was the largest species of Tyrannosaur that we know of existed, and probably was the largest that existed of all time. It also sits as one of the largest land predators to ever exist. The adult-sized Tyrannosaurus was about the size of a school bus, measuring roughly 12 meters in length, and it weighed anywhere from 8 to 14 metric tons, depending on which formula you kind of use to calculate the body mass. And compared to many other theropod dinosaurs, fossils of Tyrannosaurs were actually pretty common throughout the world, with dozens, or throughout North America, with dozens of these specimens having been found over the years. And this includes several fairly complete skeletons. And these specimens have been found all across North America, ranging with the farthest northern occurrences actually being in Alberta, near a town called Huxley. And these the range extending at least as far south as New Mexico and Texas, with teeth that are potentially identifiable to Tyrannosaurus rex, also having been found in Mexico. And because we have so many specimens of Tyrannosaurus rex, we've learned actually a lot about the biology of Tyrannosaurs and Tyrannosaurus rex in more specifics. But in Alberta itself, Tyrannosaurus rex are actually quite rare, with at present only about 3 specimens of even remotely complete skeletons having been found in the province. The most famous of these being known as Black Beauty, and this specimen was discovered back in 1980 by a group of young boys while they were fishing after school. And at first they thought that they were just finding these small black fragments of bone that were coming out of the hill. And they actually showed them to their teacher, and who actually kind of realized the significance of these. And so they called the Royal Tram Museum, who was only just then being built. And then the Royal Tram Museum launched a full excavation of the site and found a very well-preserved, nearly complete Tyrannosaurus skeleton there. And this marked probably one of the most important discoveries of a Tyrannosaurus skeleton in Alberta, just because it was basically one of the first instances of a T-Rex being found in the province. Much more common among Alberta's tyrannosaurs is Gorgosaurus, and fossils of this species are quite abundant in Alberta's Dinosaur Provincial Park. And this species is represented by one of the best tyrannosaur fossils that has ever been found in the world, which is on display at the Royal Trail Museum if you've ever been there. This specimen is known as the famous death pose Gorgosaurus, and the way you can see it here is actually the way that it was found in the ground, with it having that very prominent curled structure there, as well as all of the bones you see there actually being real. So this is actually one extremely complete specimen, and it's a beautiful specimen to see if you ever have the chance to go to the Royal Trail Museum. You won't regret it. And this specimen is basically right as soon as you get into the gallery. So it's a beautiful specimen, and I've had the opportunity to study it that I'm greatly proud of there. Now, because Gorgosaurus fossils are so common, this species has been extremely important for helping us to kind of suss out some of the details of tyrannosaur biology that are much more difficult to test within the typically typically more rare species. And so one of these is in helping us to understand how it is that tyrannosaurs grew, or how it is that they changed from adolescent to adult. And so because of this, we've been able to make some pretty important discoveries about tyrannosaur growth. One of the most important of these is that tyrannosaurs actually had these two different body forms depending on their age. The smaller juvenile or adolescent tyrannosaurs had these incredibly long legs with much more slender proportions. Their skulls were narrower, their teeth were more blade-like, and these were much better suited for slicing through flesh than they were for crushing through bone. But as they got into their older adult growth stages, or as they started to mature, they started to take on these much more stockier body forms. So their bodies were much more heavily built. Their legs were a lot shorter with respect to their actual body proportions, and they just had much more powerful jaws that were capable of delivering those bone crushing bite forces. So there was a change that went on through their growth. And so these extreme differences between the overall builds of these juvenile and adult tyrannosaurs actually suggest that these different age groups likely had different ecological roles, with these smaller and fleeter-footed juvenile animals likely preying on smaller and faster prey, such as the oviraptorids or those ostrich-mimic ornithomimid dinosaurs like I was talking about earlier, where those adults were preying on slower and heavier prey like the horned ceratopsids or the duck-billed hadrosaurs. And so this highlights a very interesting ecological dynamic where tyrannosaurs were actually dominating multiple predator roles throughout their lifetime, ranging from those apex predators that we see in the adult growth stages to those lower tier predators as juveniles. And this is quite different from what we see in other dinosaur-dominated ecosystems, as well as different from some of our modern ecosystems where different species occupy different ecological roles. For example, compared to the African savanna, juvenile tyrannosaurs would actually be occupying a role that was similar to cheetahs or leopards, where the adults were occupying the apex predator role that lions would be more like today.
Can I interrupt real quick?
Absolutely,
we have a
yeah.
question in the chat about clarification. So
Okay.
it sounds like you're saying that Tyrannosaur is a genus, a family. What's the classification here?
So I guess I should have clarified that. Yeah, so Tyrannosaur is kind of the generic term for the entire group. It's basically, we just kind of use it as kind of a throw around term. It's basically like anything that is closely related to T-Rex or more closely related to T-Rex than any other dinosaur. The Tyrannosaur lineage is basically a huge lineage that basically spans around 100 or about around 100 million years potentially, if I remember that correctly. I could be wrong on that age date exactly, but it's a very long time that these animals were around. But there is a specific genus, which is Tyrannosaurus, but the group itself, Tyrannosauroidea, that we call tyrannosaurs, or more specifically within that group, Tyrannosauridae, that we call tyrannosaurids, which I'm kind of referring to here as the tyrannosaurs, encompasses a whole bunch of different species that are very similar to Tyrannosaurus or closely related to Tyrannosaurus rex itself.
Thank you.
Okay. All right. So what's interesting about Alberta's geology is that we have this really complete sequence of rock layers that all produce fossils of different tyrannosaur species. And this reflects several different instances of these things called faunal turnovers, where basically the apex predator tyrannosaur species will last for a few million years and then will be replaced by some other species. And so this spans from about 77 million years in age to around 66 million years in age. So a record of about 11 million years where we have different tyrannosaur species just kind of replacing each other every so often. But despite how complete this fossil record may seem, we've known for years that there were gaps in this fossil record, even here in Alberta, with one of the most troubling of these gaps coming from anything older than this 77 million year marker bed in the formation known as the Old Man Formation. And this is not just an Alberta specific gap. Tyrannosaur fossils from between 90 and 77 million years of age are actually pretty rare throughout the entire world. And in fact, there have only been two other very fragmentary skeletons that have been found from any rocks dating to this interval interval to date anywhere else in the world. And what makes finding Tyrannosaur fossils from this gap so important to Tyrannosaur researchers such as myself is that before this gap, Tyrannosaurs were these very tiny fleet-footed predators, even at maximum size. And then after this gap, they were these gigantic bone-crushing apex predators. So if we want to know how Tyrannosaurs made this jump from these very small fleet-footed tyrants to these much larger apex predator species, we have to start looking for fossils within this gap. Now, thankfully in Alberta, we actually have a few rock layers which do correspond to that gap interval. And one formation in particular is a unit known as the Foremost Formation, which covers a very large area in southern Alberta. And rocks from this unit formation date to around 78 to 80 million years of age. So from anywhere from 1 to 3 million years older than our current oldest Tyrannosaur fossils that we have in the entire province. The unfortunate side to this, however, is that fossils from this unit are actually pretty rare compared to some of the other formations in Alberta. At least compared to some of the other formations that we have in Alberta. In years past, there have been 2 dinosaurs that have been discovered in the unit that were complete enough to distinguish from other fossils that can be found throughout the province. These being from a horned dinosaur that was named Xenoceratops, which is known from fossils from the frill there, as well as a dome-headed dinosaur that is closely related to things like Pachycephalosaurus, and this species is known as Colepiocephaly. And so this tells us that there are diagnostic fossils in this formation, but other than these two species, identifiable dinosaur fossils that have been largely unknown from the formation, with only a few isolated Tyrannosaur teeth having been found there in years past. But this actually changed around 2010 when a friend of mine by the name of John DeGroot found skull bones of a Tyrannosaur from this formation along the shore of a river called the Bow River near his ranch in Taylor, Alberta. And from there, the Royal Trail Museum was contacted and they came and collected the fossils for storage and safekeeping. And so this is what we have of that specimen. We actually have decent amount of the upper and lower jaws, as well as some parts of the bones that form around or that form the kind of the margin of the eye cavity. We also have some bones of the brain case, so things like the top of the skull roof, those sorts of things. So these are all bones that are actually really useful for identifying species. And so this specimen actually sat in a cabinet at the Royal Trail Museum for about 10 years. And during this time, the specimen was actually identified as an already existing species known as Daspletosaurus turosus. And it wasn't until 2018 when I was at the Royal Trail Museum working on a separate Tyrannosaur project looking at some of those baby Gorgosaurus that I was talking about earlier, that I noticed that this animal had features that were unlike what we see in Daspletosaurus or in other Tyrannosaurs more generally. For example, on the upper jaw, we found that the upper jaw bones there had these very prominent ridges that were raised along, that were kind of in a sequence, a very patterned sequence along the upper jaw. And we don't see these kinds of ridges in any specimens of Daspletosaurus that have ever been found in the province or elsewhere in places like Montana. So this was an immediate kind of red flag that this was something different. We also noted that the cheekbone was a lot thicker and more rounded in the region located below the eye socket than we saw in Daspletosaurus, which always has a much narrower margin there, with the top edge being tapered into this very blade-like kind of fashion that you can see kind of modeled there in black, with the bottom specimen there is the Daspletosaurus and the top there is this Tyrannosaur from this Foremost formation. And so we even have this specimen CT scan to see if we can figure out what was going on there. And we found that where Daspletosaurus has this very small air pocket in their cheekbone, this new Tyrannosaur was a lot larger, or had a much larger air pocket, and this possibly caused the bone to bulge out in that region. And so despite missing a decent amount of the animal's skeleton, we realized that from all of these bones that we had there, that this species was unique from all of the tyrannosaurs that we've been found before. And so we were actually able to give this a new name. And so with that being said, we had to give it some fun, edgy name. And so we came up with the idea with the name of Thanatothrystes, which the name means the reaper of death. And so to thank John de Groot and his family for making this discovery and reporting it to the Royal Trent Museum, we also gave it the species name de Grootorum to kind of honor his family there. So Thanatothrystes was a large tyrannosaur, being about as large as most of the other tyrannosaurs that we find fossils of there in Alberta. But of course, not quite reaching the size that we see in some of our largest tyrannosaurs like Tarbosaurus, Zhucheng tyrannus, and of course, Tyrannosaurus rex. But still a very large apex predator, something that I wouldn't want to meet personally. And so the fact that Thanatothrystes was this larger bodied tyrannosaur it does actually help to narrow this gap in our tyrannosaur fossil record ever so slightly and push back that gap, just to show us that that tyrannosaurs were starting to, or had already acquired those very large body sizes around 80 million years ago. Now, what's particularly interesting about Thanatothrystes or the features that it has is that it actually shows that Thanatothrystes had a bunch of features that were kind of intermediate between this Daspletosaurus, which is more common, which is something that we find a lot of fossils of in North America and never find any fossils of in elsewhere in the world, like Asia, and this more Asian type lineage that we see in things like Tarbosaurus, Tyrannosaurus, and another tyrannosaur called Zhucheng tyrannus, which can be found in China. And in particular, it exhibits characteristics of both these two separate lineages, with one of those again being that North American tyrannosaur like Daspletosaurus, and the other being that Asian tyrannosaur like Tarbosaurus and Tyrannosaurus rex. And so we have a whole swath of features that kind of just show that mixing of the two. And so what this might mean is that, and while we're not fully confident of the exact position of where this falls in the family tree, we do know that they're very closely related to both species, and so it's very possible that Thanatothrystes could fall very close to the split between those two there. So it might be closer to Daspletosaurus, or it might be closer to Tyrannosaurus, or those more Asian lines. So one of the big questions there now is to kind of finding more fossils. Can we help to better pin down just where it falls on the Tyrannosaur family tree? It's also possible that it's completely that is actually ancestral to both of these lineages, so that it's not as closely related to either or, and that Daspletosaurus may actually be more closely related to those Asian tyrannosaurs than Thanatothrystes itself. In either scenario, what this would actually tell us, or what this might suggest to us, is that this particular species could be really important for helping us to understand the geography of tyrannosaurs, or how it is that those tyrannosaurs evolved. And so what this might suggest is that around 80 to 79 million years ago, a tyrannosaur very similar to Thanatothrystes or maybe Thanatothrystes itself either had a very large range that spanned across both North America and Asia, or alternatively, it crossed over from North America into Asia across a land bridge there, and then basically set up two populations, one within North America and Asia. And over time, this North American and Asian populations would have become separated and isolated from one another, resulting in the evolution of entirely different species in those different areas, with things eventually rising like Daspletosaurus here in North America, and then those Asian species like Tarbosaurus and Zhucheng tyrannus arising there in Asia. Then around 67 million years ago, we had a really interesting occurrence where Tyrannosaurus itself seems to have may have came back into North America, and later going on to dominate almost the entirety of Western North America shortly before going extinct during the asteroid impact that would have wiped out the dinosaurs. So Thanatothrystes has the potential to actually provide us with a very interesting window into the origins and biology of those two separate tyrannosaur lineages. And this is something that the discovery of additional specimens will undoubtedly help to clarify further, and is actually one of the reasons why I've been doing a lot of field work in the area that could produce additional fossils of this particular species. So Thanatothrystes is not just important to helping us to understand tyrannosaurs specifically. Its discovery also plays a much larger role in helping us to fill in the gaps in our understanding of the dinosaur-dominated ecosystems of prehistoric Alberta, prior to those better understood intervals, and just how those ecosystems changed over time, becoming the later and better known ecosystems that are preserved in things like Drumheller or Dinosaur Provincial Park. And so this is one of the things that we're expecting, is that after finding similar types of dinosaurs in these older rock layers, we expect that we'll find similar layers or levels of diversity some of those better known formations, if we can get out and just look around in some of those more poorly known formations. So we have a lot to learn about formations like the Foremost Formation, that we're slowly starting to fill in with those gaps with additional fossil discoveries. And so what we can guess right now, based on those few dinosaur, oh, sorry, that was something that I already talked about. And even more than the Foremost Formation, if we actually go older down in those rock layers, we actually have some other dinosaur-bearing rock layers where you can find isolated teeth and other fossils that aren't quite as useful for identifying fossils. But a few years ago, in this one formation known as the Milk River Formation, which is even much older than the Foremost Formation where fossils of Thanatharistes are coming out of, a few years ago, there was a fossil of a dome-headed dinosaur that was identified as being completely different from all the other dome-headed dinosaurs that have been found anywhere in the world, that was able to be identified as a completely new species, and it was called Acrotholus. And so this actually tells us that formations like this Milk River Formation do preserve fossils that are diagnostic and might actually have some other fossils of other dinosaurs that can be found there in the future. And what's important to me, or important to my research, is that this formation in particular has actually produced a few isolated tyrannosaur teeth. And so we know that there were tyrannosaurs here. We just don't know what species they are, because unfortunately teeth are not very good, are not good enough on their own for helping us to establish species. But it's also very likely that these teeth came from something completely different, a completely new tyrannosaur species, given their size and their shape. So myself and some of my colleagues have really started to focus on that formation as well, to try and suss out if we can find some tyrannosaur or additional tyrannosaur fossils from that formation, to see if there are maybe some other species there that we are currently unaware of. And so with that, and beyond the Milk River Formation, there are some other poorly explored and potentially fossil-bearing rock formations that are elsewhere in Alberta that potentially correspond to time periods that nobody has even started to look in terms of what fossils might be there. And so it's even potential that we might find fossils of some of these other tyrannosaur dinosaurs, some of the smaller, more primitive dinosaurs there yet. But one of the problems that we paleontologists encounter is that a lot of the places that we want to look are quite remote, and we unfortunately can't devote a lot of the time to looking in those new fossil localities. And some of those areas are very likely to have some fossil discoveries in the future. It's just one of those things of just having to get out there. So I think that the future of Tyrannosaur paleontology and dinosaur paleontology in Alberta has some great potential, and I'm hoping that in the future some of these discoveries can be made that can really help us to even more improve our understanding of the biology of these animals. And so with that, I'd like to thank a bunch of people who have been greatly supportive of funding sources and that sort of thing. And I'd also like to thank all of you for helping me out during this presentation. And with that, I'd be more than happy to take any questions if you have them.
There was another one in the chat.
Okay.
Has it ever been decided on the idea of T-Rex with feathers or proto-feathers / quills? It's a controversial topic.
So we know that ancestral tyrannosaurs closer way down the line, so several hundred or several tens of millions of years older than Tyrannosaurus and the other tyrannosaurids, so the large body tyrannosaurs, we know that they had feathers. We've been able to find fossils that actually preserve feathers, and even some of the larger animals that were, again, really early on. But as for fossils from the Tyrannosaurids, so like T-Rex, Gorgosaurus, and Thanatharistes, those sorts of species, we have never been able to find skin impressions that preserve anything that looks like feathers. It's not to say they're not there. It's just that our skin impression fossils, or the molds that we have of skin impressions, that sort of thing, right now, we don't have any impressions of feathers yet. They could be there, but we have to basically get more complete stuff. I'm still looking for a Tyrannosaur mummy. There's got to be one out there somewhere. Somebody's got to find it eventually. I know it's out there.
So I'm actually wondering if you could talk a little bit more about the role of specimens that are already in collections in terms of discovering new stuff. As a person who works in a museum, like, we've got a basement filled with objects, some of which have been cataloged, some of which haven't been looked at in 50 years. So how important is it? And are there people whose main role is to sort of comb through museums and try to find that, like you thought it was a Daspletosaurus, but it turns out to be a Reaper of Death, which is totally the name of my next metal band, but that's neither here nor there. But so can you talk a little bit about, like the role of existing collections and discovering new species?
Absolutely, and that's actually the important part. Most of kind of the research that's done, especially for graduate students such as myself, most of the research there is stuff that we are are based on fossil discoveries that have been made way earlier on. A lot of the fossils that I'm working on were found in the 80s and early 90s, that sort of thing. And that's just because that was when the Royal Shore Museum was really starting to get built and when a lot of our fossil collections started to go. But in fact, personally, I've never actually found a really complete Tyrannosaurus skeleton myself. So I do a lot of research on Tyrannosaurs, of course, but most of the work that I'm doing is on stuff that was found 4 or 5, 10 to 10s or 20 years ago, right? So I'm basically going around to museums and looking at things that have already long been discovered and trying to make comparisons there. And so, yeah, basically that's most of my research itself is just looking at stuff there that's already been found. So it's probably, I would say that's more important than even, I don't want to say it's more important than going out and doing digs themselves, but there's a lot of fossils out there that need to get examined. So that's one of the things that I do when I go to museums is kind of just look around at what they have of stuff and see, okay, is this important? Is this a really important thing? And I say fairly frequently, a lot of the stuff that's kind of thought of being like, oh, it's not worth it, actually has some specific scientific value.
Neat. Nice. There's a couple other questions that have come in on the chat here. First of all, do Tyrannos occur elsewhere on Earth aside from North America and Asia? How widespread are they generally?
Yes. So again, kind of going back to the actual semantics of what Tyrannosaur is. The actual useful definitions: Tyrannosauroidea, Tyrannosauridae. Tyrannosauridae being the really large apex predator forms that I mostly study. Tyrannosaurids have only been found in Western North America and Asia so far. There are some really closely related what we call non-tyrannosaurid tyrannosauroids that were really closely related to those really larger those giant apex forms that we find in Alberta and Asia, that are just a little bit smaller and don't fall within our classical definition of Tyrannosauridae proper, that can be found in along the Appalachian subcontinent in places like New Jersey, which was the famous Dryptosaurus, which was found back in the 1700s. And also a more recently named species known as Appalachiosaurus down from Alabama. And there's probably a whole bunch of other tyrannosaurs there. But as we currently know it, Tyrannosauridae itself was limited to Western North America and Asia, just because there was some interconnection going on there. The much larger group Tyrannosauroidea, which was around for several tens of millions of years, there are fossils of Tyrannosauroids in Europe. There's a couple of them on the in the UK itself. There are Tyrannosauroid fossils or potential Tyrannosauroid fossils in Australia and potentially even South America. So it's possible that the larger group Tyrannosauroidea had a cosmopolitan distribution across the entire world. We still don't have a really good handle on that, but they definitely spanned across from Europe, Asia, and North America.
Nice. Another question. What about making, you showed some CT scans of the dinosaurs. Any pushes to make those scans freely accessible to researchers online?
They absolutely will be. Or at least it's a weird situation there where the Royal Shore Museum owns kind of like the CT data itself, but two researchers, once we're finished up with this project here, which should be fairly soon, we're basically at the last leg of getting this thing published or submitted for publication. But once that's all done, the CT data for that project will be at least hosted with the Royal Shore Museum to researchers to access, and potentially, but I'm not 100% sure, there might be just hosted on like a public data repository like Dryad or something like that, which is something that I've used in the past. One of the projects that we worked on recently, if you have interest in CT data, One of the papers that are recently published on tyrannosaurs, we actually published some CT data of specific sections of tyrannosaur jaws, mostly of the palate region. And if you go look on my ResearchGate, you can get a link to that file there, and that'll have some of the CT data from the palate regions of some of those tyrannosaur fossils. But other stuff will be online eventually, I promise. It's just we got to get it all published first.
Yeah, it's exciting. Yeah, yeah. Another question has come in. How do you determine the amount of smushing that has occurred in a skull? That's a highly technical term. Hopefully you can interpret smushing for us.
Mostly it's kind of just like, oh, that looks to be smushed. There are certain structures that a lot of times, so one of the things we oftentimes look for within different things is with tyrannosaurs, we know that they had very wide skulls. And there are also certain structures within the skull that can actually give us an indication of how much of that smushing is going on. So the foramen magnum, which is basically where the brainstem comes out of the brain cavity at the back of the skull. In most animals, that foramen magnum is very circular in shape, or at least the depth dimensions are about the same as the width dimensions there. There are some exceptions. But in tyrannosaurs, we presume, and it seems to be the case, that in our least deformed specimens, that it's a very circular shape. So if we see a foramen magnum that's very squished in some dimension, we can kind of get an indication of how much smushing went on in that. With some of our baby tyrannosaurs in particular, the smaller ones that get preserved, we oftentimes see a lot of that smushing going on, with that foramen magnum being very narrow. And in addition to kind of that plastic deformation going on in the skull that actually can result in like the actual different dimensions there, you also can oftentimes get a lot of brittle deformation. So you'll see like cracks or stuff like that kind of show that it wasn't this narrow in life. And in fact, most of the time, some of the best fossils are the ones where, for actually getting a metric of how wide or some of the actual dimensions of a skull that were when they were in life, come from fossils that were disarticulated. So the Royal Troll Museum has a really nice specimen of Displetosaurus. And if you actually go after this, if you go look online, you can actually see in a 3D representation of all the skull bones and where they fit. Those are very unsmushed because they were basically all found isolated together. And so we can actually piece those together digitally or in real life and get an actual measure of how wide the skull was there.
What would be the website that we could go to see that?
Let me actually see if I can pull it up. I can just post it in a link.
That would be awesome.
I know the Royal Troll Museum actually posts it on Sketchfab. And I've actually used it multiple times because sometimes it's a lot easier for me. I have a lot of photographs of the specimens. But getting the 3D model, I actually go here a lot of times for when I'm doing research. It's like, oh, what was that feature like in 3 dimensions? And so I come here to look at it, even though sometimes I actually have the
I feel like a lot of folks here would be interested in that. While you're looking for that, we've got 2 other questions, if you don't mind. So I'll do the first one. Oh, thank you. There it is in the chat. Perfect. So a question about how to define a new genus.
Yes.
Question they say can apply to any fossil group. How subtle or obvious are the differences? What's the point where you say this is new?
Yes. The genus distinction is entirely subjective. If you actually go and look at the ICZN's website, they're at the ICZN's website, they actually talk about like what defines genera and stuff like that. And they don't really have a good definition. Species is basically pretty obvious. It's basically if you have features that are different from any of the other established species, that's it. For when we established our genus, we actually went back and forth on that. I can't tell you how many times. It was basically like, oh, today I'm just going to say it Displetosaurus digrutorum. This day I'm going to say that the Thanatharistes. The reason that we ended up going with a new genus was because we had such a back and forth of different characteristics between things like T-Rex, Tarbosaurus, and Zoochain and Displetosaurus. We actually didn't, the phylogenetic tree that we recovered showed it as being closer to Displetosaurus, but a lot of that we interpret as being because we have a really good record for Displetosaurus, and there's a huge gap behind that. So it's artificially, those phylogenetic trees are going to pull it to one of those branches one way or another. So it's kind of identifying what defines a species or a genus is really up to subjectivity. There's also the issue with the ICZN. If someone were to come along later on and establish that, if we were to say it's Displetosaurus digrutorum, and then someone were to come along later on and they name it something else because they realize, oh, well, our phylogenetic analysis recovered as something completely different. We basically lose essentially we lose the naming rights to the taxon, or in a roundabout way, we lose a lot of the kind of the name rights to the taxon. So if it gets sunk later on into Displetosaurus, that's perfectly fine.
And I feel like that happens a lot where people learn a name that is no longer like the common name, a name that was used like in the 1960s or something, and we don't call it that anymore. They just, A couple of other questions here. So one that's interesting to me, there's a person who's interested in filmmaking who wants to know if you'd recommend any documentaries about the Tyrannosaur species of Alberta. And then after that, there's a couple of other questions about their behavior.
Yeah, so the best documentary that the documentary that I liked the most was Prehistoric Planet. I think that was what it was called, right? Like the most recent one. I think that's what it was called. I can't remember.
This is the David Attenborough one on
that one.
BBC.
I absolutely love that one. So that was what I would recommend. It was just phenomenal.
You can't go wrong with David Attenborough.
Exactly.
I mean, the man could like read the phone book and I'd be like gripped by it. But
as for the diversity of Tyrannosaur species, there really aren't any documentaries that go over all of the different Tyrannosaur species as we know them. There could be some in the future, but as far as I'm aware, there haven't been any that have gone really in depth over the different Tyrannosaur species. A lot of times the papers themselves, I feel like, are really good for kind of establishing those themselves.
Cool. So then one person asked about the hunting behavior of tyrannos. Did they hunt on land, also in or near water, and also did they migrate? You mentioned them leaving North America and coming back. I don't know if that was what you would call migration or just a long-term behavior, population shift over time. After that, I think a related question is about rearing their offspring. We know about adults and juveniles. Do we have much or any info on the babies or the eggs?
I wish we did. I'll start with the migration parts. We really don't know. The problem with trying to identify behavior in the fossil record is a lot of times behavior is not really well preserved. Some of the only things that we really have from behavior in terms of their hunting behaviors are from bite marks on bones of potential prey items, or in a lot of cases, in one specific case, heel bite marks, or in a couple of cases actually heel bite marks of prey items like duckbill dinosaurs that got away. There is one duckbill dinosaur in a Montosaurus that actually has a part of a Tyrannosaur tooth actually embedded in one of its tail vertebrae, and then that healed over. So that indicates that there was a failed predation attempt there. As for how far they range for their hunting, we don't know. Large predators can oftentimes have very large ranges to hunt around in terms of their modern counterparts. So presumably that would have been the case for Tyrannosaurs as well. They would have had very large ranges. To that point, one of the very interesting things is that there seemed to be, one of the things we've kind of noticed with Tyrannosaurs is that there's potential for at least during the Campanian, around 76 million years ago, it seems like there were some of these different Tyrannosaur species. We had about 3 to 4 different species of Tyrannosaurs that were all coexisting along Western North America potentially at the same time. So they might have had very small species ranges. We don't actually know all that much about that yet. It's something that I've kind of been investigating a little bit here and there, but it's really difficult to do with how spotty the fossil record can be. As for the rearing their offspring sort of thing, we have next to no information there. Juvenile Tyrannosaurs are extremely rare. I'll pull it up really quick here. Let me find the slide for it. Slide. Nope, not that one. Give me 1 second to get back. Not that way. But kind of just go over it while I'm doing that. We don't have that many very young Tyrannosaur fossils. So these two right here, these 2 Gorgosaurus specimens that were found, are the 2 most complete young Tyrannosaurs that have ever been found in North America. At that same point, or by that same token, however, I don't know if I have a measure of their size. These things were still about the size of a horse. So they were still very large animals. They were probably around 5 to 7 years of age. Getting much smaller than that, we're basically basing our entire fossil record on isolated remains. And there are a few isolated remains. There was a couple, about 2-3 years ago, there was some of my friends actually published on the lower jawbone of a very young, potentially hatchling or even an embryo tyrannosaur from Montana. But we honestly otherwise don't have that much data on really, really young tyrannosaurs. We have no eggshells whatsoever from tyrannosaurs, or no eggshells that we can actually identify as tyrannosaurs confidently. We have no nests of tyrannosaurs either, nothing of that sort, no gravid tyrannosaurs, nothing. So our understanding of tyrannosaur brooding behavior, how if they raise their offspring, is extremely limited to the point where it's basically non-existent at this current moment. It's one of the things that I'm very much interested in. I would presume there was some rearing behavior, but again, I have no data whatsoever to back that up. So that's just me conjecturing completely.
But it's awesome that there's so much you still don't know, right?
I know,
mean,
right?
that makes it interesting and exciting.
Exactly.
Other questions? Thank you, Jared. That was fantastic. Really interesting. Appreciate your time so much. Good luck with the rest of your research, and I look forward to learning more about your finding your papers that you've published and following your work in the future.
Yep, likewise. It's great to be here. If you guys ever want me to give a presentation again, hopefully I'll have some other dinosaur groups here in the near future that I'll be talking about that will have some other really cool projects there. So yeah, it was great giving a talk to you guys.
Sounds excellent. Thanks so much. Take care.
All right, take care. Have a great time, everybody.